Hello, everybody. Welcome back to Mathematical Statistics. We have been talking about the Cramér-Rao lower bound, which is a lower bound on the variance of all possible unbiased estimators of a thing. I will remind you of the notation and what that thing is today, but the Cramér-Rao lower bound is part of our broader topic of maximum likelihood estimation, which we will get back to today. So last time we stated and proved the Cramér-Rao lower bound. I'm just going to quickly recap it, and then we're going to do some computations. So for the Cramér-Rao lower bound, we have an x1 through xn, and they could be IID, but more generally, they're assumed to have some joint PDF, f of a vector x and theta, which could be vector valued, but for what we're doing with the Cramér-Rao lower bound, we're going to keep it simple, and we're assuming that theta is one-dimensional. It doesn't have to be. There is a higher dimensional Cramér-Rao lower bound. But for now, we're just going to assume it's one-dimensional. And we want to estimate either theta or some function of theta. So we call that tau of theta, and tau of theta might just equal theta. And we have any unbiased estimator. So we would normally call such a thing tau hat, but because it's a statistic like a maximum or something like that, something computed from the data, for Cramér-Rao lower bounds, it's generally easier to think of it with statistic notation. So I've got some capital T, which is some function of the vector of data. So the Cramér-Rao lower bound says that the variance of T is greater than or equal to tau prime of theta, that's a derivative with respect to theta, all squared over the n-dimensional Fisher information. And this Fisher information term is named after a statistician named Ronald Fisher. It is the expected value of the derivative with respect to theta of the log of the joint PDF with the capital X's plugged in so that there is randomness and theta. And we're going to square this whole second derivative and then close this expectation. So again, this is the Fisher information. And this thing on the lower side of the variance of t, where t is n, the unbiased estimator of tau of theta, this is known as the Cramér-Rao lower bound for tau of theta. We usually use a subscript like this. Okay, so we did all this last time. Let's get to an example. I'm going to keep it simple for my first example. I've got an x1 through xn, IID exponential with rate lambda. And there's going to be two parts to this question. One is find the Cramér-Rao lower bound for the variance of all unbiased estimators of the rate parameter lambda. That is a mouthful, and a lot of times people will say, find the Cramér-Rao lower bound for lambda, and that's okay as long as you know what it means. It's not a lower bound for lambda. The quote-unquote Cramér-Rao lower bound for lambda is a lower bound on the variance of all possible unbiased estimators of lambda. And in part B, we're going to find the Cramér-Rao lower bound for the variance of all possible unbiased estimators of lambda squared. I want to just remind you that Fisher information is, there's a whole subject called information theory, but the thing for you to remember here is that if you look at the circled Cramér-Rao lower bound, the tau function only appears in the numerator. And in my example, we have two different tau functions. And so part B is actually going to be very quick, a very short problem once we've done all the work in part A. And then the denominator contains all of the information about the data. So that's kind of why it's called an information term, although information has a broader meaning. But for now, we'll just think of it as containing all the information in the data. All the x's are in here, which are in the denominator, and the denominator has nothing to do with tau, and the numerator just has to do with tau and not the data. Okay, So let's go for that Fisher information. We're going to need it for both A and B. This is the expected value of the partial derivative with respect to theta of the log of f of capital X, that's the joint PDF, squared, and close that. So let's build up this expression. The f of x and theta for the exponential is lambda e to the minus lambda x, and an indicator saying that x is between 0 and infinity. So here's where I'm going to maybe contradict myself. Um, we did see last time that the Cramér-Rao lower bound does not apply whenever the parameter is in the indicator. So if there is a theta over here in the indicator, forget trying to compute a Cramér-Rao lower bound. It doesn't have meaning in that case. And we've talked many times about taking the log of a function and taking the derivative of a function. If there's an indicator in there, you're not taking the log or derivative of that part. Remember, we've talked about like a piecewise defined function with regions indicated. And if you were to take the derivative, you would take the derivative of this, and those would be your answers over this region and this region, but you wouldn't take the derivative of these guys. So the same thing is happening in indicator land. We don't take the derivative of the indicator. And if we did, it's constant with respect to theta, and that part would disappear. My point is this. I say, oh, always use indicators, always use indicators. I think it's easier to just sort of ignore them for Cramér-Rao lower bounds. The only time they're really super important is if the parameter is in there, and then we wouldn't be computing a Cramér-Rao lower bound in the first place. So I'm going to ignore them. We need a joint PDF. And because our random variables are IID, we'll get this by multiplying the individual PDFs. And they are right here. Sorry, I keep writing theta out of habit, but the parameter here is lambda. I guess it would be fine to leave a theta if we defined theta to be lambda. Okay, so when I plug in the circled thing and multiply them out, I get lambda to the n, e to the minus lambda to the sum of the xi. There's the joint PDF with the indicator sort of ignored. So again, working towards the Fisher information expression, I now want to take the log of this. This looks a lot like likelihood stuff and finding the MLE, and it's related, but it's different. The log of this expression is going to be n log lambda minus lambda sum of the xi. Next, if you look at the Fisher information, we want to take a derivative with respect to lambda. So computing a Cramér-Rao lower bound is very plug-in chug formulaic. At the end, there's an expectation, which you might have trouble with sometimes, but usually, yeah, it's very plug-in chug. The derivative with respect to lambda of the second term is the negative sum of the xi. And we are ready to write down the Fisher information. I don't think I changed that lambda. Here should be a lambda. This is the expected value of the square of this thing with capital letters plugged in. So I am going to flip this around. Because I'm squaring it, it doesn't matter, and I think this looks a little nicer. But that's just the thing in the circle squared. And to find this expectation, we could square this out and run the expectation through, but we'll have a sum times a sum, and it's going to get pretty ugly. But if you're lost and you have no other options, then go for it. But we do have other options because right here is the sum of NIID exponential random variables with rate lambda. So we know this has a gamma distribution with parameters n and lambda. And then this is the mean of our gamma distribution with parameters n and lambda if you parameterize it the way we do in this course. So this is a gamma random variable minus its mean squared, and then the expectation. This is the variance of a random variable w, where w has the gamma and lambda distribution. And so if you recall or go to your table, the variance for our gamma distribution is alpha over beta squared, but in our case, alpha is n and beta is lambda. So this is the n-dimensional Fisher information. Okay, so I think I wrote part A. I didn't write anything to the start here, and that's kind of good because this is the denominator for both parts A and B. And in part A, we've got this as our tau of lambda. And in part B, we've got this as our tau of lambda. And again, the only place the tau appears is in the numerator of the Cramér-Rao lower bound. So all the hard work was in finding that Fisher information, and it's the same for both A and B. So watch out for this on the upcoming exam. If you did a kind of a long problem and then there's a part B where you have to find a Cramér-Rao lower bound for something else, it's probably as simple as this. Let's write these down. If tau of lambda is lambda, then the Cramér-Rao lower bound for tau of lambda is tau prime of lambda squared over this n-dimensional Fisher information. It's one-dimensional thing. I say that, but it's the Fisher information based on all n pieces of data. And so continuing, the derivative of this with respect to lambda is 1, so I get 1 squared over n over lambda squared, and we get lambda squared over n. For part B, we want the Cramér-Rao lower bound for the variance of all unbiased estimators of lambda squared. So now the Cramér-Rao lower bound, still the same setup, but the derivative in the numerator is going to change, and that's all that's going to change. Again, we did all of the hard work above. So this is 2 lambda squared over n over lambda squared. So it's going to be 4 lambda to the 4th over n. And we are done. Right now, for the beginning of today's class, I just want to stick to the plug and chug computation. But eventually we're going to use this to compare variances of estimators. For example, the MLE, the maximum likelihood estimator for the exponential, is 1 over x bar, which is biased. But if you compute the variance of this, don't remember what you get. I don't think I want to do it. You're going, well, actually, it's meaningless against the Cramér-Rao lower bound because this is a biased estimator. I was going to say if you compute the variance, it should be greater than or equal to the Cramér-Rao lower bound for lambda, but that's not true for this example because this is a biased estimator. So why are Cramér-Rao lower bounds so important for maximum likelihood estimation? Because I'm going to write it down eventually in a list. So this is kind of a one-off. That's not going to make any sense. But if theta n hat is an MLE for theta, we're going to show that under certain regularity conditions, MLEs are asymptotically normal, with mean equal to the thing you're trying to estimate and variance equal to the Cramér-Rao lower bound for that thing. So it's like, in some sense, the variance of your estimator is approaching that Cramér-Rao lower bound, which is not exactly right. Wait till I get to the list. This is why I care about Cramér-Rao lower bounds in the context of MLEs, even though Cramér-Rao lower bounds are only for unbiased estimators and MLEs are often biased. In the limit, they're becoming unbiased. They are asymptotically unbiased, and I'm getting way ahead of myself. So this was our first example of a Cramér-Rao lower bound, and I promised you some computational simplifications. Okay, I have 3. The first one is that if you look at the expected value of the thing that looks like the Fisher information, but is not squared, you get 0. So I want to show this. I think last time we did the whole notation where we're integrating against a vector. So I'm going to need that sort of thing here. The left-hand side, so this is the proof. How would you compute this? this is a function of the vector of x's. So this is going to be the integral, which is really an n-dimensional integral of the function with the lowercase x's plugged in, and then multiplied by because it's an expectation involving the vector of x's, we need to integrate against the PDF for the x's, and we're going to integrate over the whole space. This is really n integrals, all from minus infinity to infinity. And then what is the derivative of the log of something? It is the derivative of the thing over the thing itself. So we get the derivative with respect to theta of f of x and theta over f of x and theta times f of x and theta dx. We're going to get some cancellation, and now I have an integral of a derivative. Now I don't just want to cancel, right, because one's with respect to x and one's with respect to theta. So I am going to pull out the derivative, and because we're doing a Cramér-Rao lower bound simplification, we are assuming that we can do this. This was one of 3 so-called regularity conditions required for the Cramér-Rao lower bound to hold. So we're assuming we can bring that derivative in and out of the integral. But now this is an n-dimensional integral of the joint PDF over the whole space, and that is going to be 1. And the derivative with respect to theta of 1 is 0, and that's what we wanted to show. So this is computational simplification number 1 that you're not going to really use that much directly, but I need it to prove the next 2 computational simplifications. And just while we're here, I will write this down later when it becomes really important to us. But this thing in here is known as a score function. You might see it denoted by like an S of x and theta, something like that. The name score function actually goes back to Fisher. He was a statistician and geneticist, and he was doing some kind of study, and he was assigning a score to different families, a certain score depending on whether or not they had a genetic trait. And that's sort of the origins of the terminology score function for this piece. Hopefully that'll make more sense eventually. And right now we don't need to call it anything, but I will come back to it where we will call it the score function. The expected value of the score function is always 0. Okay, computational simplification number 2. This says that the expected value, so basically I'm writing down our Fisher information, get this whole guy squared, is equal to the negative of the expected value of the second derivative of the thing not squared. This is a great simplification. When you take derivatives of things with respect to, say, theta, often they get simpler as a function of theta, but sometimes a derivative could make things worse. So we're going to do a lot of examples, and I think you're going to choose this simplification often, but you don't have to. So let's prove it. So by property 1, we have the expected value of this score function is 0. Okay, let's write out this expectation. This is the integral minus infinity to infinity, the derivative with respect to theta of the log of f of the lowercase vector x and theta times f of x and theta, because it's an expectation, so we want to integrate against the joint PDF for all of the x's in there, and the right-hand side is still 0. So now I want to take the derivative on both sides with respect to theta, and I'm going to pull the derivative inside the integral. And then I want to take the derivative of the product of this and this. So I'm going to do like a product rule for derivatives. So we get the first thing, which is d theta log f of the vector x and theta times the derivative of the second thing. So d theta f of x and theta plus the second thing times the derivative of the first. I am going to go ahead and run the integral across this thing. So let me close this one out. And I'll get plus the integral of the derivative of this, which is the second derivative, fx theta times the PDF. Again, this is just a product rule derivative, and the right-hand side is 0. Okay, I'm hoping to see something. And the thing we're trying to prove up here is all in terms of expectations. So let's make sure we have some expectations here. The second term is already an expectation because you see the PDF here. So this second term is the expected value of the second derivative with respect to theta of the log of f of capital X and theta. The first integral, I'm not integrating with respect to or against a PDF. I'm integrating a function against the derivative of a PDF, but it's not going to be an expectation until we do one of our log tricks here. So I would like to see an f of the vector x and theta in here. And so to get this, I could take well, note that the derivative with respect to theta of the log of f of x and theta is equal to the derivative of f of x and theta over f of x and theta. So I can put this in if I also divide by it, so I don't really change anything. And then this is equal to this. So the whole thing up here is another copy of this. So I get this squared in front of this joint PDF and integrated. So let me write that. We have the integral, the derivative with respect to theta of the log of f of x and theta squared times f of x and theta dx plus, I'll go write the second one out as the expectation. We already know it to be, and this whole thing equals 0. That's still the right-hand side. But now the top line of this equation here is the expected value of the derivative with respect to theta of the log of f of capital X and theta squared plus blah, 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 blah. So take this and subtract it to the other side, and we're done. We have shown that this is equal to the negative of this, which you get right from this equation. So we're done proving property 2. Like I said, I think you're going to really like to use property 2 and property 3. But sometimes property 2 will make the problem harder. Most of the time it won't. And we're going to get to our examples, but let's write down property 3. So everything we've done so far has assumed that x1 through xn comes from some joint PDF. And they maybe were not IID. But if they are IID, so if they each have the individual PDF little f of x and theta, then I claim that the n-dimensional Fisher information, if they are IID, is equal to n times the one-dimensional Fisher information. So where did the n come from? This Fisher information is the expected value of the derivative with respect to theta of the log of f of the vector x and theta, all squared. And then this one-dimensional Fisher information is just this, but with like an x1 in there, not a whole vector. x1 or x2 or x5. They're all IID, so it doesn't matter which one you look at. So in the IID case, you can compute an expectation involving just one of the x's. So in the previous example where we had the exponential distribution, we ended up working with a gamma distribution because our expectation had a sum of exponentials. But if we never had to deal with that sum, everything would be a lot easier, especially in upcoming problems where we won't necessarily know the distribution of a sum right off the bat like we did. And both of these could be rewritten in the second derivative notation. So you don't have to square anything before taking the expected value. So you might use simplification 2 and or 3 or, in tandem or separately, but let's prove this. Let's prove it. So V, n-dimensional Fisher information, is the expected value of the derivative of the log of f of the vector x and theta squared. If they're IID, then that joint PDF has a nice form. We get the product as I goes from 1 to n of f of capital Xi and theta. Those are different functions because the f up here takes an n-dimensional argument and the f down here takes a one-dimensional argument. So the log of our product is the sum of logs. Let's write that. And let's square this out. I am going to write, let's bring this, this derivative inside and then square this out. So we're going to end up with the sum as I goes from 1 to n of the derivative with respect to theta. Actually, I'm not going to square it out. I'm just going to write it down twice. And we'll square it out in a moment. So I could write the same exact thing again, but it's just a sum of things, and so it's going to be convenient to give it a different index. Okay, so I could pull like this whole thing inside this sum, and you end up with a double sum. So this is the expected value of the sum. I'm not going to pull it that direction, actually. Just going to draw or write the I sum first. And then d theta log f xi and theta d theta log f xj and theta. And I can pull these sums out of the expectation because it's a linear operator. And I don't even have to give this any special thought about infinite sums exchanging with that integral or sum that the expectation is. Everything's nice and finite. So let's go ahead and pull these out. And I really should copy and paste this, but it was kind of sloppy. So let me write it one more time. Boy, this is looking bad, but it's gonna turn around and start looking simpler very soon. Okay, so note that we have n squared terms here. Whenever I'm doing a double sum like this, I kind of think of them as the terms arranged in a matrix, an n by n matrix. And so we have n terms in the diagonal, and that's where j equals I. And then off the diagonal, so in the case that j does not equal I, if we wanted to look at this expectation, just said I wasn't going to write it again. Let me copy this. When j does not equal I, then this is a function of xi and this is a function of xj, and they're not the same x's. So in this case where j does not equal I, these are independent. And that means that we can write this as the expected value of first one times the expected value of the second one. But each of these are the expected values of the score functions. This is 0 times 0 by computational simplification or property 1. So this is saying that if you imagine this as the ijth entry of the matrix, everything off the diagonal is going to evaluate to 0. And then on the diagonal, so let me bring this down here. We're left with just the sum as I goes from 1 to n of the expected value of the derivative with respect to theta of the log of f of xi and theta times the same thing, but with I in for j. So we really end up with this squared. And this expectation is with respect to just the ith x. So this would involve an integral against the PDF for xi, but x1, x2, x3, they all have the same PDF. They're IID. So these expectations are all going to be the same. Just real quick, if you were to write this down, you'd get an integral, real quick and sloppy, x theta, and then an f x theta dx. And this is the same PDF for all of them. And these are just dummy arguments. This expectation is going to be the same thing for every I from 1 to n. So because they are identically distributed, this is n times the expected value of one of these. But that is the one-dimensional Fisher information. That's the Fisher information without the vector, but instead just an x1. So we started with, way up here, the so-called n-dimensional Fisher information. And in the IID case, we got n times the one-dimensional Fisher information. So we are done with the proof of this property. Let's go back to our exponential example. So the previous example, let's just look at part A. We had x1 through xn, IID, exponential with rate lambda. And we wanted to find the Cramér-Rao lower bound for a tau and another tau. And really, it came down to the Fisher information, which took a bit of work. But now we can say, because these are IID, this is n times the one-dimensional Fisher information. This one-dimensional Fisher information is the expectation of the derivative of the log of f of x1 and theta squared. And it's also the negative of the expected value of the second derivative without the square. So which one do we want to use? Let's look at the PDF. I keep writing theta, and these should be lambdas. Sorry about that. The PDF is lambda e to the minus lambda x. The log of the PDF is log lambda minus lambda x. The derivative with respect to lambda of the log of f of x and lambda is 1 over lambda minus x. So two options. I'm going to do it both ways. If I take this back up to the top, I want to compute the expected value of this thing with a capital X plugged in, x1 or x5 or whatever, and squared. So this is 1 over lambda minus x1 squared, which is also, because it's squared, x1 minus 1 over lambda squared. But this is the mean for the exponential. So this whole thing is the variance for the exponential. And that is 1 over lambda squared. So going back up here, the n-dimensional Fisher information is n times 1 over lambda squared. It's n over lambda squared. And that's what we got before when we did this the long way. And that's the denominator for the Cramér-Rao lower bound. And it was a lot easier dealing with just a one-dimensional random variable. But this will get even easier still if we instead go with this version for the one-dimensional Fisher information. Because down here at the bottom of the board, I have the first derivative. So now I'm going to take the second derivative with respect to lambda. So that first term is lambda to the minus 1. So you get minus lambda to the minus 2, or negative 1 over lambda squared. And then with respect to lambda, the derivative here is 0. So check this out. The expected value of this thing with a capital X plugged in should be a 1. This is the expected value of the negative of 1 over lambda squared. Now, there's no randomness in there. So this is just like saying the expected value of 5 is 5. It's a constant, and we just get that constant. Going back up to the pink-purple circle, there is a negative that's supposed to be in front of this. And so you end up with this again. You get the negative of 1 over lambda squared. So going back up here, you get the same thing for your Fisher information, which is going to be the denominator for your Cramér-Rao lower bound. Let's do one more example from scratch rather than just matching up with an example we've already done. Suppose that x1 through xn are IID Pareto with parameter gamma. And I want to find the Cramér-Rao lower bound for the variance of all unbiased estimators of the gamma parameter, or just to make this slightly more interesting, this function gamma minus 1. Let's do it. We want to find that Fisher information, the n-dimensional Fisher information as a function of little gamma. Because we're IID, this is n times the one-dimensional Fisher information, and let's work it out. So the PDF, f of x and lowercase gamma, is gamma over 1 plus x to the gamma plus 1. And yes, an indicator that says that x is between 0 and infinity, which I'm just going to kind of ignore, just because it's not clean to bring it through the logs and the derivatives. So now we could do a joint PDF and go directly for the n-dimensional Fisher information, but I'm going to go for the one-dimensional one. So we need to look at the log of this. And we get the log of gamma minus the log of the denominator. And for that denominator, I'm going to bring the exponent down in front of the log. And let's take a derivative with respect to gamma. We get 1 over gamma plus the log of 1 plus x. I can tell you right now that you're going to want to take that second derivative, because this ugly expression is going to disappear when you take the derivative with respect to gamma. So let's take the second derivative. And we get negative 1 over gamma squared plus 0. So the one-dimensional Fisher information is the negative of the expected value of this second derivative, which is the negative of the expected value of negative 1 over gamma squared, which is the negative of 1 over gamma squared, because this is a constant. There's nothing random there, which is 1 over gamma squared. So the n-dimensional Fisher information, because we have IID things, is n times the one-dimensional Fisher information. And that's going to be n over gamma squared. So remember that our function of gamma was gamma minus 1. And the Cramér-Rao lower bound for this function is the derivative of the function squared over the n-dimensional Fisher information. And the derivative of this, just multiply it out. It's gamma squared minus gamma. We'll get 2 gamma minus 1. That whole thing ends up squared over n over gamma squared. Again, we're just sticking with computation for today, but we are going to eventually find, look at the MLE for the gamma parameter and see how its variance might be approaching the Cramér-Rao lower bound. And I have that list coming up really soon. So we're done, but what if we didn't take the second derivative? Just want you to know that you could do this. You know how to do this. If you wanted to take, so alternatively, if you wanted to take the expected value of the derivative with respect to gamma of the log of f of x1 and gamma squared, this would be the expected value of gamma minus the log of 1 plus x1 squared. And I would turn this around. I just think it looks a little more familiar if you turn it around. How could you deal with this? You could look at, oh, I don't mean xi, although that's not really wrong, but I just kind of mean to fix one of them. You can define this to be, and sorry, I think I copied this wrong. Yeah, this should be 1 over gamma right here and here. If you go to find the distribution of y, doing the G inverse kind of thing, and you work out the PDF, we've done this one a couple of times now, and I don't expect you to have memorized it, but you could go do this on the side here, and you would end up with gamma e to the minus gamma y, an exponential random variable with rate parameter gamma. So this y up here has the exponential distribution with rate gamma, and 1 over gamma is the mean of the exponential distribution with rate gamma. So overall, I've got the expected value of like, well, let's go straight to the variance. I've got the variance of y, where y has an exponential distribution with rate gamma. And the variance for the exponential is 1 over lambda squared, in this case, 1 over gamma squared. And so doing the sort of more difficult expectation, we did end up with the same thing as doing that second derivative version, using our skills from the beginning of the course, realizing that this is something whose distribution we know, and we can recognize this expectation as a variance. You almost always can rewrite your Cramér-Rao or rewrite the Fisher information in terms of a variance of some distribution. If it's not a distribution that you know and have tabulated, then it's not that helpful. But yeah. Okay, so we will be doing many more Cramér-Rao lower bound calculations, but I do want to get to a list of nice, here was the whole point, nice properties of maximum likelihood estimators. So suppose that we have x1 through xn IID from a distribution with a PDF that depends on a parameter theta. And again, we're going to assume that theta is only one-dimensional here. I'm going to let theta hat be an MLE for theta. And actually, I want to change this notation just a little bit because we want to talk about some asymptotic properties as n gets large. All of our MLEs depend on the sample size, like 1 over x bar. This was a sample or a sample mean of n things. So I am going to go back here and put a subscript on here to really emphasize the dependence on n. Otherwise, nothing's changed. It's just a new notation. So under certain regularity conditions, we have a bunch of properties. Number one is that the MLE exists and is unique. Number two, the MLE is a consistent estimator of theta. And that means, as you'll recall, that it converges in probability to theta. What are the regularity conditions? They are well, it depends on which number we're in. So as we go through and prove these, we will pick out the conditions that we need and create a big list that you can have for future reference, although you're not going to need it for this course. But if you go on and do more advanced mathematical statistics, I think it's going to be a good list to have. Theta n hat is asymptotically unbiased for theta, and this means that the limit as n goes to infinity of the expected value of theta n hat is going to approach theta. Now, some MLEs are actually unbiased straight away, in which case this will just be theta, 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 and the limit of that sequence will be theta. But in general, they will not be unbiased. So you're going to get some kind of function in here of theta and n. And if you let n go to infinity, it will go to theta. So that's what we mean by asymptotically unbiased. For, I forgot to define something. I'm just going to, I'll come back and talk about this right after this list. This theta n hat is an asymptotically efficient, this is the thing I haven't defined, estimator for theta. So what this means, I forgot to define efficiency, is this is the idea that the variance of your estimator is approaching the Cramér-Rao lower bound in the sense that it's getting as low as it can go as the sample size gets large. So that actually doesn't make sense. I'm going to write that and then cross it out. I kind of want to say the limit of the variance of the estimator is equal to the Cramér-Rao lower bound for theta. Like in the limit, it's becoming unbiased, and the variance is getting as small as possible for unbiased estimators. But this line doesn't make sense because our Cramér-Rao lower bounds actually depend on n as well, and n is supposed to have gone off to infinity. So this is the idea. The variance is approaching the Cramér-Rao lower bound, but we have to say it like this. The limit as n goes to infinity of the Cramér-Rao lower bound for the variance of all unbiased estimators for theta divided by the variance of the MLE is going to 1. This alone without the limit is what it means for an estimator to be efficient. The variance has achieved or is equal to the Cramér-Rao lower bound, and so that ratio is 1. That's what it means for an estimator to be efficient, but the MLEs are guaranteed to at least be asymptotically efficient. So let me finish this list and then I'll write down the definition of efficiency. Fifth thing is that under certain regularity conditions, the MLE is asymptotically normal with the correct mean and variance equal to the Cramér-Rao lower bound for the variance of all unbiased estimators for theta, i.e. theta n hat minus theta over the square root of the Cramér-Rao lower bound for theta is approaching in distribution a normal 0-1 distribution under certain regularity conditions that, again, we will figure out when we prove this. Okay, so I actually am not going to get into the proof today because I'm running out of time. I do want to give you the definition of an efficient estimator. So I'm going to put like a squiggly line thought break here. I'm not talking about MLEs at the moment. Here is a definition. Suppose that theta n hat is an unbiased estimator for theta. It doesn't have to be an MLE. We say that theta n hat is an efficient estimator for theta if the Cramér-Rao lower bound for the variance of all unbiased estimators for theta over the variance, or theta n hat, is equal to 1. If it's unbiased, it makes sense to compare its variance to the Cramér-Rao lower bound. The variance is always greater than or equal to the Cramér-Rao lower bound, so in general, this thing is less than or equal to 1. But if it's an efficient estimator, this thing is going to equal 1. And then we define the efficiency of an unbiased estimator as this Cramér-Rao lower bound over the variance of the estimator, which again is always less than or equal to 1. And this is assumed to be unbiased, or it really doesn't make sense to be comparing the variance to the Cramér-Rao lower bound. If you computed a Cramér-Rao lower bound and then you had a biased estimator, you could actually get the variance below the Cramér-Rao lower bound in some cases, in which case this thing would become greater than 1. And so I don't like to talk about efficiency in that case at all. I think it only makes sense for unbiased estimators. But if you want to, you would say then that you have a super efficient estimator, something whose ratio of the Cramér-Rao lower bound to the variance is actually greater than 1. But with this definition of efficiency, now the asymptotic efficiency maybe makes more sense, because both the numerator and the denominator of the thing I just circled depend on n, so you'll get some ratio depending on n, and if you let n go to infinity, if this ratio goes to 1, then you have asymptotic efficiency. So the very last thing is that I'm going to fit in is I want to start proving those things in those nice properties of MLEs list and also give you the regularity conditions along the way. We're going to need an inequality that I meant to cover a month ago, but I skipped it because I was kind of pressed for time and we didn't need it at that point. And that was when we were talking about Markov's inequality and Chebyshev's inequality. There was a third one, which I'm going to talk about now, called Jensen's inequality. So this is usually stated in terms of a convex function g. If it's convex, that means it's concave up like this. And that means that all tangent lines to the function, no matter where you put a tangent line, is going to be completely below the function. Okay, so I'm going to consider a random variable x with some mean mu. And I'm going to consider a tangent line at mu, and this would be g of mu. So this line, I haven't stated Jensen's inequality because I always get it backwards, so I kind of need to derive it every time, and that's what I'm doing. This line is the line y equals some slope x minus mu plus g of mu. And this is always less than or equal to g of x. And this is since g is convex. So I'm going to use this inequality here, and I'm going to plug in capital X's, the random variable, all the way across. And now I'm going to take the expectation all the way across. And I guess that's something we should prove. What does it even mean? I don't have time today, but what does it even mean for one random variable to be less than another? It actually means that this holds with probability 1. And in that case, the expectations will hold. Please just, I will talk about it next time. So assume you can take the expectation across this inequality and the inequality holds. So on the first term, we get this slope expected value of x minus mu. But if you run that expectation across, this is the expected value of x. Sorry, I'm rushing. This is mu minus mu. This expectation is 0. This is constant. It is g of the expected value of x, and that expectation has already been averaged out. So the expected value of g of mu is just g of mu, and that is g of the expected value of x. And on the right side, you get the expected value of g of x. So here it is. Here's Jensen's inequality. For a convex function, g, the expected value of g of x is less than or equal to g of the expected value of x. I am out of time. This is usually the way it is stated, but you can also state it for concave functions, which are things that are concave down. And yeah, we'll do that next time. But I am out of time, so we'll finish talking about Jensen's inequality and about what's going on here about expectations running across inequalities. And we'll go back to our list of really cool properties of MLEs and start proving them next time on Mathematical Statistics.